Hello everyone, my name is Paul and I'll be speaking about quantum materials making smartphones cool again. So if your cell phone or laptop has ever overheated, could you please raise your hand? Right, take a look around. We've all been there. As our devices become smarter, they're generating larger and larger amounts of heat. All of this heat causes a decrease in performance, reduces device lifetimes, and translates to a huge waste in energy. In fact, it's estimated that in just a few years, up to 1/5 of the world power will be consumed by an estimated 20 billion internet-connected devices. This includes cell phones and laptops, in addition to different types of internet servers, advertising, and the expanding Internet of Things. With everything from self-driving cars to even smart egg trays, we live in an increasingly connected world that places higher demands on our environment. To understand why our electronics are consuming more power and generating more heat, we're going to see today that over the past 2 decades, we've simply been cramming more computer chips into our devices instead of making them faster and more efficient. Now, at the heart of every modern electronic device is a fundamental building block known as a transistor. We'll go into more detail later, but for now, we can essentially model a transistor as a switch. When the switch is on, we get a 1, and when it's off, we get a 0. For anyone who's ever seen movies like The Matrix, you know that these 1s and these 0s are incredibly important. They comprise a code known as binary and are the fundamental language that computers use to operate. Now, historically, these transistors, these switches have taken on a variety of different shapes and forms. ENIAC was the world's first electronic computer and was developed right here at Penn in the 1940s, just across the street. One of the main reasons that ENIAC weighed a massive 30 tons and occupied a room just as large as this one was because it contained 20,000 of these switches, each resembling a light bulb the size of a human hand. Over time, developments in manufacturing have allowed us to miniaturize these switches. To give you an idea of just how far we've come, a typical computer chip today contains around 2 billion transistors. This trend, known as Moore's Law, states that every 2 years, the number of transistors in a computer chip will double. Predicted in 1965 by the founder of Intel, Moore's Law has held true for nearly 6 decades and is one of the great marvels of semiconductor manufacturing. The blue line on this graph demonstrates how over time, the number of transistors per computer chip has steadily increased. However, you'll notice there's another line on this plot. The black line represents a speed of a transistor. You'll notice that for a few decades, it goes straight up, and then starting around 2002, goes completely flat. Now here lies the fundamental reason why our phones are on fire. Instead of improving the design of transistors to be faster and more efficient, we're simply stuffing more and more of them into our devices. This is obvious if you've ever taken a look at a computer and seen words like dual core, quad core, or even deca-core. So as a final step today, let's take a look at why building a better transistor is such a difficult problem and how ongoing research in quantum materials hopes to overcome some of these obstacles. So this schematic shows the basic idea behind a transistor. If we recall from before, a transistor is essentially a switch. When the switch is off, we have a 0. And when it's on, particles are able to travel from point A to point B, and we get a 1. Now, instead of going into the boring details, we're going to use a very handy analogy. A transistor is just like a house. In order to get a 1, our friend, we'll call him Ben, needs to go from point A to point B by going through the house. Now the problem is that when Ben goes through the house, he's allowed to take any path that he wants. He can go straight on the first floor, or he can go up to one of the top floors, wander around for a bit, and then come back down. When Ben goes up and down the stairs, his body consumes a lot of energy, it generates a ton of heat, and he starts to sweat. And this causes your phone or your laptop to overheat. Moore's Law over the past 6 decades has been focused on packing the same Moore's Law over the past 6 decades has been focused on packing more and more houses into the same amount of space. But no matter how densely we pack these houses, the underlying process is still inefficient. Ben will still not take the most direct path. Until now, researchers here at Penn and around the world are focusing on a new class of compounds known as quantum materials. Using these materials ensures that every time Ben goes from A to B, he takes the most direct, most efficient path. The end result is a transistor that's not only faster, but consumes less energy and generates less heat. Quantum materials themselves have uncovered a wealth of new and groundbreaking physics due to their unique one-atom-thick structure. They are 300 times stronger than steel, tougher than diamond, and weigh less than paper. These phenomenal properties have generated tremendous interest in the tech industry and have the potential to revolutionize electronics as we know it. So honing inspiration from great Penn scientists like Ben and the innovators of ENIAC, researchers like myself hope to use these quantum materials to truly transform our digital world. Let's really be smart and keep the Earth cool, one phone at a time. Thank you.